In this discussion, we continue to discuss about two more elementary flows, namely doublet and point vortex, and we will also discuss about the concept of a vortex sheet. So, in the previous lecture, we had discussed about the second elementary flow, that is a source flow or a sink flow, and we discussed about the details of the same. We move on to our third elementary flow, which is called as doublet. As we develop the concept, the previous elementary flow, that is source and sink concept, will be useful for us. So, let us say that we have a uniform flow approaching a pair of source and sink of equal but opposite strength. So, you have a capital lambda here and a minus capital lambda here, which means this is a point source, this is a point sink, and they are separated by a finite length L. If this is a situation, then we have a potential flow past a so called Rankine oval. These are nothing but streamlines of the flow, and this forms the so called dividing streamline, and we can have a psi equal to 0, that means the stream function value is allocated to 0 on that dividing streamline. Now, if you were to limit the gap between the source and the sink to 0, what would happen? They would virtually merge to a single point or nearly a single point, where the gap is infinitesimal. But as you reduce the gap, if you keep a parameter kappa given by the product of the spacing or the gap and the strength of the source or the sink in a modulus sense constant, then you have the strength of the doublet defined using kappa. Now, in the limit as L tends to 0, basically you would end up having kind of infinity minus infinity strength singularity. But though this is indeterminate, it can still have a finite value. Now, let us bring the source and the sink extremely close to each other and see how the flow patterns look. The streamlines would emerge like this, and lobes would be formed. This is how the flow pattern will look like about the doublet. Now, if you place a field point P at r theta from the doublet, then this is the radial distance, this is the angular orientation theta, etc. So, you can say that as a function of r theta, you can express the stream functions and the vorticity potential. Sorry, the velocity potential, not the vorticity, but velocity potential. So, this is the stream function, this is the velocity potential. So, we are not proving them here, but I would encourage you to explore further as a homework that how you can derive these, because you already have the basic concepts. Remember that you have to work in r theta coordinates, cylindrical polar coordinates. Now, using this concept of doublet, we can look at the flow past a cylinder. Where at the center of the cylinder we place a doublet, which would create the patterns that we already looked at. And on that we superimpose a uniform flow. So, as you may recall that we are handling Laplace equation, which is a linear partial differential equation, and the different solutions can be superimposed. What the superposition of uniform flow over a doublet produces is so called non-lifting flow past a cylinder. Non-lifting flow past a cylinder. Why non-lifting? Because there is no circulation, there is no vorticity present in this flow. Therefore, there is no mechanism by which potential flow can model lift. Now, you might be wondering that what about the radius of this cylinder? How do we define the radius of this cylinder? What is the extent of this cylinder? Of course, the extent of the cylinder is defined by this streamline with the associated stream function phi equal to 0. This, as I mentioned earlier, is called as the dividing streamline, because on one side of it you have the free stream, on the other you have the flow inside the cylinder, which is by virtue of the doublet, and this streamline divides the two. Now, as far as the radius is concerned, the radius of the cylinder can be shown as under root kappa by 2 pi u infinity. That is how the radius of the cylinder can be quantified. So, the kind of flow that you are looking at is a completely attached flow, because potential flow always remains attached to the body. There are no near wall viscous effects, no boundary layer, and flow slips on the surface. That means there is no slip condition. There is no wake, since the flow does not separate. Additionally, we have a front stagnation point and we have a rear stagnation point. There are another two very important things that we need to mention, that is, we will see soon that the pressure distribution on the top portion of cylinder equals the pressure distribution on the bottom portion, and thus there is no lift generated by the cylinder. By top portion, what we mean is this portion, this is the top, and by bottom we mean this. So, there are so many important facts that we are trying to see over here. Additionally, pressure distribution on the front half, that means the one which is facing the uniform flow, is equal to pressure distribution on the rear half, and the consequence is there is no drag acting on the body. So, we will very soon see through the pressure distributions why all these things happen. The fact that there is no drag acting on the cylinder, which is very contrary to what we see through real life experience when we immerse a cylinder into the flow, is called the so called D'Alembert's paradox. So, the potential flow predicts that there is no drag acting on the cylinder, while real experimental situations always predict a drag. There is a difference between the two, there is an anomaly between the two, that is what is referred to as D'Alembert's paradox, because all real experiments, all real computations predict non-zero drag. That is the reality. So, this is a theory which has some assumptions, some approximations, and by virtue of that we find that there is no drag. Now, how did we get to this pressure distribution at all? Now, what the doublet produces is, or rather the combined doublet uniform flow produces is V r equal to 0 and V theta is equal to minus 2 V infinity sin theta velocities on the surface of the cylinder. That means, anywhere on the surface of the cylinder, the radius of the surface of the cylinder being given by the expression that we already written in the previous slide. At that radial distance, the flow slips, as we already discussed, and the value of the flow velocity is given by this, which is just the tangential component. And remember that the flow is moving this way. That is something that you have to keep in mind. Now, going by this expression, remember that we consider theta from here. So, when theta varies between let us say 0 is less than theta is less than equal to pi. So, that is basically the top part of the cylinder. What is happening is that in this region the sin theta is positive, and therefore, the V theta, which is considered to be positive in this direction, will just take the opposite direction, because as you can see the direction indicated by the streamlines is just opposite to this. These are opposing directions. So, the negative sign basically creates the direction this way, which is consistent with the streamline indication. While when you go to the other part, the lower part of the cylinder, how does theta vary? Theta should be varying between pi and 2 pi in the lower part. So, this could be called as top, this could be called as bottom. So, in the bottom part, the v theta direction will be along the theta direction itself, and that is consistent with the direction of the streamline. Therefore, this is a consistent expression which gives the direction of the v theta appropriately. From there we get C p in the form of 1 minus v by v infinity square, which is 1 minus 4 sine square theta. Now, what does this indicate? If you look at that expression of C p, if you are plotting C p along the y axis, if you are plotting theta along the x axis, so this would be minus pi by 2 minus pi. So, basically this is the bottom half, this is the top half, and if you look at the pressure distribution, how it varies, it is equal to 1 here, then by the time you reach pi by 2, it drops to minus 3. By the time you reach pi, it again recovers back to 1. That is how the 1 minus 4 sine square theta expression works. Similar things would happen on the other side. It drops to minus 1 here at minus pi by 2, and it recovers back to 1 when you move to minus pi. So, this is how the pressure distribution turns out to be symmetrical about the bottom and top, and therefore, there is no CL. CL is equal to 0. Similarly, try to see how it is between the rear and the front. So, the rear half is basically spanning between minus pi by 2 and pi by 2. So, that is the rear half, and these two segments, this one here and the other one here, these comprise the front half. You will find that there is no imbalance between the rear half and front half as well, and the consequence of that is that C d is equal to 0. So, if you were to take the C p expression and integrate it over the body, considering that this is an inviscid flow and therefore, C f will be 0 anyway. So, you just take the C p distribution and integrate it over the body surface, you can get the expressions for C n and C a, the normal force and axial force. They should also be equal to 0. Now, we were talking about the real life experience that the drag is always non-zero. So, in real life, how does it work out? If you immerse a cylinder into the flow and you have a uniform flow approaching like this, then the flow separates from the rear part of the cylinder, creating a wake. This part of the flow is viscous dominated, and if you try to plot the C p distribution on the body surface, this time as a function of, let us say, let us define a different angle. Let us say from the front stagnation point, we try to define an angle, let us say phi, and we indicate the phi over here. Then you will find that the C p distribution looks more like this for the real flow past a cylinder, where the flow is separated in the rear part of the body, while the theoretical C p distribution may go down like this to reach the minus 3 point at pi by 2 and so on. So, the anomaly between the theoretical pressure distribution and the real pressure distribution through an experimental effort or a computational effort creates differences between the forces, and we find that the difference is basically produced in the drag. the lift remains 0, at least in a time average sense. Why time average? Because very often these flows are unsteady. There is vortex shedding behind the cylinder. Vortex structures leave the surface of the body once flow separation takes place and moves into the wake, and these shed alternately from the body, and thereby it produces undulations in the forces which act on the body. That is why we said time average forces. So, the lift variation may look like this when CL is plotted along the y axis and this is the time axis. So, when you take a time average, then you find that the lift comes out to be 0, but the time averaged drag, the drag also being a function of time, does not come out to be 0, it is always greater than 0. Typically, the drag may be of the order of 1, the drag coefficient, again depending on the Reynolds number range. So, we say that there is a subcritical range where it is of the order of 1.2 or so. There is a supercritical range where it can be lower, maybe of the order of 0.8. So, this is all about the doublet, and now let us introduce the fourth elementary flow, which is called as a vortex flow, or we can also say point vortex flow. And when we have multiple of these vortices arranged, we will see that can lead to a so called vortex sheet. Now, why are we so very interested with this elementary flow? Because we would soon see that superposition of potential flows involving point vortices leads to finite lift generation. So, up to this we were never talking about a situation where circulation was produced, but now we will see that a vortex flow produces net circulation, and typically a point vortex would be represented by an arrow like this, indicating that it induces V theta, not V r. And then we will see that if you lay these point vortices one after the other along a curve, then they can form a sheet of vortices like this, which we will call as a vortex sheet. Later on you will see that we will talk more about thin airfoil theory, where we try to model the potential flow past an airfoil by considering it to be very thin and approximating it with its camber line, and we try to represent the camber line as a vortex sheet. Now, coming back to a single point vortex and its influence on the neighboring flow. So, this is the point O, where we are locating a point vortex, and these are streamlines of the flow, where each streamline is associated with a V theta, which is typically represented by an expression C by R. Each streamline can of course be represented by a stream function. So, the stream function values would vary from one streamline to the other. So, what we find is that the V theta is inversely proportional to R, where R of course is the radial distance. So, if this is a field point R theta, this is the radial distance. The V r is equal to 0. Note that in the case of a source or sink flow, we had purely V r and we had no V theta. If we were to calculate the circulation along a streamline, we pick any one of these streamlines and we try to calculate the circulation around it, it is a closed curve. So, we do this calculation and what would we find? The v will be constant, that is v theta times 2 pi r, that is the integral of ds. Let us name this as equation 1, that this is equation 2, and let us rewrite this equation and name it as 2a, let us say v theta is equal to minus gamma by 2 pi r. So, now if you compare equation 1 and 3, what do you get? You get c by r is equal to minus gamma by 2 pi r, which implies that c is equal to minus gamma by 2 pi. Now, basically the equation 4 indicates that circulation taken along any streamline is constant for that matter, because the gamma is equal to minus 2 pi c, the gamma is constant. What is this gamma? This gamma is the strength of the point vortex. Which is located at point 0 or rather O. Now, we had discussed in an earlier lecture that as per mathematical convention, the counterclockwise line integration is considered to be positive. But then again in aerodynamics, the clockwise circulation is considered to be positive. So, their sense is opposite, and the negative sign in the gamma expression basically takes care of that difference in the signs. Now, vortex flow is irrotational. All over in the field, apart from the point O. We can actually prove it formally. So, in general it is irrotational, but it is not so when you try to see the rotationality about the point O. So, if you imagine that you have a very small surface, say ds, about the point O in the form of a streamline which is nearest to the point O, then curl of the velocity vector can be represented in terms of the constant c and the ds using this equation. Where do we get this expression from? The expression for gamma can be applied to that very small element surrounding the point O, and then from there you should be able to get this expression. Now, from this expression which we have very close to the point O, what happens is that as r tends to 0, you are already very close to the point O. This is what your ds is. That means, r is tending to 0 anyway. So, as r tends to 0, what happens to ds? ds also tends to 0. And then what happens to curl of the velocity vector? It tends to infinity. That means, you have a singularity. So, that singular point is the point vortex, and you do have rotationality. Surrounding the point O. That is the point we are trying to make here. Now, for vortex flows, del phi del r, which is V r, is equal to 0, that we already discussed. Additionally, 1 by r del phi del theta, which is giving you the V theta, that is given by minus gamma by 2 pi r. So, from these expressions you can obtain the phi to be equal to minus gamma theta by 2 pi. So, that is the velocity potential for your point vortex. Similarly, by taking derivatives of the stream function also, you can express the velocity components. And what does that give you? That gives you information about the stream function. So, from these relations you get the stream function equation to be this. So, you now have the expressions for velocity potential and stream function for a point vortex flow. Now, coming to an application, we saw earlier that when you combine doublet with uniform flow, what do you get? You get non-lifting flow. Why non-lifting? Because CL was equal to 0, non-lifting flow past a circular cylinder. So, we had summed up the phi for the doublet, the phi for the uniform flow, and you got it. And then if you sum it up with the phi for the point vortex, then what do you end up getting? You get lifting flow past a circular cylinder. That means, addition of the point vortex brings in circulation, which is connected with the lift. How do the flow patterns really look like in that case? So, you can imagine the cylinder which is formed due to the interaction of the doublet with the uniform flow, and now you have additionally the point vortex, which brings in the effect of circulation. The moment it brings in that effect, the streamlines get bent, they become completely unsymmetric, and they now can be looking like this. So, you already have the doublet out here, mind it. You also have the uniform flow far upstream, and additionally you now have the point vortex. So, the doublet is somewhere here, additionally you have the point vortex. Let us indicate in a different color. So, the sum total effect is like this, the streamlines lose symmetry. Now, if you were to look at the V theta now, the earlier V theta, which was purely due to the doublet and uniform flow combination, it was this, and now you have an additional component which is by virtue of the point vortex. So, this is the effect of the point vortex on V theta. What will be the effect on Cp? So, Cp is 1 minus V by V infinity whole square. So, Cp will turn out to be so you can see some additional terms coming over here by virtue of the presence of the point vortex, and the additional terms are easy to figure out, they are these. So, the earlier non-lifting flow was just comprising of this part, while this is the lifting part. Obviously, you can figure out that the symmetry in Cp distribution will be lost, loss of symmetry because of the additional term. And how does it reflect? It reflects on a situation where, of course, we continue to say that Cf is equal to 0 because it is an inviscid flow. But what about the effect of Cp? It has no effect on Cd. Mind it that Cd and Ca are the same because alpha is equal to 0 degree. So, how do you find Cd? Of course, it comes from the definition of Ca by ignoring the contribution of Cf. If you just take the Cp contribution for the cylinder, it comes out to be like this. How do we do it? We use a transformation. Y is equal to r sin theta. So, dy is r cos theta and C is equal to basically 2r, that is the chord. So, that is how the CA expression is expressed for the cylinder, and you will find that this comes out to be 0, which is left as a homework for you. That means, the D'Alembert's paradox holds good. What happens to Cl, which is the same as Cn? We can work it out similarly. This time the transformation has to be x equals r cos theta. Therefore, dx is equal to minus r sin theta d theta, and as a consequence that is equal to minus half pi to 2 pi C p L sin theta d theta plus half pi to 0 C p u sin theta d theta. Once you integrate, it comes out to be gamma by r u infinity. Again, this is your homework, which you should try doing. Now, remember that for a cylinder without any point vortex, the Cl was 0. It was a non-lifting case, but here Cl is greater than 0, which is by virtue of the point vortex, which has the associated circulation gamma. And then if you were to work out the lift per unit span, then that turns out to be the Cl into half rho infinity u infinity square into S into 1, which is gamma by r u infinity into the dynamic pressure. What is S? S is projected area. So, if this is the cylinder, this is the radius of the cylinder, then when the uniform flow impinges on the cylinder, it sees the dimension 2r. That is why the S is written as 2r into unit span, which is perpendicular to the page, and this lift expression comes out to be gamma rho infinity u infinity. That means, the circulation times the density times the velocity of the free stream. This expression is called as the Kutta-Joukowski theorem. In this lecture, we discussed about the doublet, the point vortex, and their application to lifting and non-lifting cases. Further, we had a very introductory discussion about the vortex sheet, where point vortices will be laid along a curve, typically the camber line of an airfoil, and then we will further take that concept forward when we discuss about the thin airfoil theory. Thank you.